Um, so today my topic is room impulse response-based spatial feature for the multi-channel multi-talker ASR. So it's part of my work that I worked this summer at Tencent AI Lab. So before I start for our proposed method, let's first review the baseline system we have. So our setting is that we will have the multi-channel microphone along with the depth camera at the center of this microphone, so that we will both get the multi-channel audio input along with the video inputs. And for the video side, we will use some vision face detection method to help us get the position of each speaker inside this picture. For example, let's use this speaker 1 as our target speaker. So from the face detection and also some geometry calculation, we can get 3 information from this target speaker. That is its azimuth, its elevation, and also its depth to the microphone array. So these 3 information we call this 3D information. And along with the multi-channel audio input Y, altogether we will send to the next feature extraction parts. So for the feature extraction is mostly the spectral feature and spatial feature. And both of them come from the STFT transformation. So the spectral feature is the magnitude from the STFT, and it's like the normal feature we have for normal ASR system like RIR-SF or F-bank. The other side is something special, which we call a spatial feature, that is from the face of the STFT. And here we have IPD and TPD. I will explain more on what is these features exactly in the next slide, but let's just keep this in mind. And after getting these features, we directly send this feature to an ASR module. And this ASR module is a common ASR module, and the only difference is its input is different. So along with the RPS of the overlap speech, we will also have the IPD and TPD. And we will do the target speech recognition on top of that. So what is exactly IPD and TPD? So IPD is the inter-channel phase difference. It's something we got from the real signal we have for different channels. Let's say we have a pair of microphone M1 and M2, and we also have their we have the audio input for them. And we take the phase of these 2 channels, and then we compute the phase difference between them. That's the inter-channel phase difference. And for the TPD, it's called the target. Okay, T is the, because we do this on the STFT domain, so the T and F is the time index and the frequency index. So it's something for the TF beams. So we do the same thing for each TF beam. Okay. So for the TPD is called the target dependent channel phase difference. So the key point here is the target dependent. That means when you have the position of your target speaker, by position I mean the azimuth, the elevation, and depth, from some geometry calculation, we can then calculate the phase difference from all the audios coming from that position. Like, let's see this picture as an example. We can calculate if we take these 2 microphones as a pair, we can then calculate the length of these 2 lines, and then we calculate the distance between them. And from some like the signal transformation things, we can calculate all the TPD, the target dependent phase difference for each frequency. And we assume that the position of the target speaker does not change during the entire utterance, so that actually this T is a fixed stuff, and only the TPD is varied for each frequency. So after we have the IPD and TPD, let's say if our target speaker is now dominating the mixture speech on a specific TF beam, then you would see that IPD should equal to TPD because all the mixture is now dominated by your target. So when you take the cosine of this difference, you will get this number close to 1. That's something we call it a spatial feature. to give you a concrete idea of how it looks like. So here is a simulated example. So on the left side, it's RPS of your target speaker 1 and the interfering speaker 2 and their mixture. On the right side, it's IPD, TPD for the speaker 1 and their cosine distance. So over here, you can see that the pattern shows in the spatial feature, that is the cosine IPD minus TPD, match pretty well with the RPS of the target speaker 1. So when you have the RPS of your mixture along with the spatial feature altogether to the ASR system, you can expect it to do a very successful targeted speech recognition.
Before you go on, you want to explain why that TPD looks the way it does?
Because you mean for this?
Middle one,
yeah. Because firstly, I said because we assume that it does not change, the positioning of the target speaker does not change through the time. So it will be a horizontal line across it. And for this axis, it's frequency. And for this axis, it is the time. And to show it better, we take the cosine of it. But actually, we don't use the cosine. Like I put it a cosine here to make this picture looks more clear to people.
But no, I think that, so you explained why they are horizontal lines. You're saying that relative to the microphone, the speaker is sitting in the same place all the time. So whatever is happening at some time is also happening. Why is it banditly?
Because let's move back to this TPD calculation. Because in this calculation, the distance, the distance difference is the same. But because the signal travel speed also depends on the phase itself depends on the frequency. So for each different frequency, we will have different phase difference, and it's like periodic stuff through all the frequency range. So that's why it looks like there's some periodical things through the frequency range. And for also, I probably need to also explain why the IPD looks like this. So in this IPD, you still see some horizontal pattern, but you will see some uncontinuous things inside this picture. The reason of this is because when the mixture speech change the components, for example, as the first few at a few frames, because the mixture is coming from the speaker 1. So the IPD is actually the same thing for the speaker 1. But when the second speaker joins in, because for this part, it now becomes their mixture, so that the IPD also changed. So you will see a pattern for IPD is like it's continuous at some short period, and then it changed to another pattern. So when you compare this IPD with the TPD, because the TPD is time invariant, then you compare these things together, you will get the pattern you show in the cosine IPD minus TPD. Yeah. But here comes the problem that when there is strong reverberation inside the room, like this reverberation I show in this picture, it look like when you have some audio sources inside the room, it actually will not just directly goes to the microphone, but it will also reflected by some surfaces inside the room. So in such example, the actual source is not only your real source, but we also have some virtual sources. That is the image of your actual source on the wall. So because of that, you would not let's assume that there are only 2 audio sources inside the room. So other than just have the direct path of X1 and X2, the 1 and 2 here denote the index of the speaker, you will also have the reverberation of them. So you will have the first reverberation, the second reverberation. And because we assume that the reverberation here is strong, we cannot ignore these terms. Then even if you assume that right now your mixture speech Y is totally dominated by your target speaker X1, you would not see the phase of your mixture equal to the phase of the your first element, because there are also some reverberation term here, and they also contribute to the phase of the mixture. And because of that, you can also not assume that the phase difference you got from Y should be equal to the phase difference you got from X. That means IPD would not equal to TPD in such cases. And because of that, let's see this example. Because we do these things on the simulated data, so here I can keep all the things the same, but only change the RT60. So the RT60 is a hyperparameter, means how the reverberation will decay by 60 dB, how long it will take. So longer this number means the reverberation is stronger. So here I raise the RT60 from 0.1 seconds to 0.6 seconds and make all the things the same. But by doing so, because the TPD is still the same thing, the TPD is we got from the position of the speaker. So it is totally the same as usual. But for the IPD, it's blurred quite a lot because, as I said, right now, because of the reverberation, there are multiple sources for each short period. Then you cannot see any small horizontal patterns in the IPD. So when you compare IPD with TPD to get the spatial feature, you can see that you can hardly find any patterns in this spatial feature. And when you combine such feature with a mixture RPS and send it to an ASR system next, you cannot expect it to get any good results. So here is the table we have for these situations. So for the first row, it is a single speaker reverb clean baseline, which means there's no overlap speech and there's also no any other noise, but only reverberation. And for each column, we change the strength of the reverberation. So for the first column, there is no reverberation at all. And the second column is that we have normal reverberation. The RT60 is ranging from 0.1 to 0.6. And the last column is when we have strong reverberation, which range from 0.5 to 0.7. And you can see that for the single speaker baseline, the ASR performance does drop a little bit by like 1% absolute, but I think it's acceptable because we don't do any de-reverberation in such a system, just showing people how a normal ASR system should react with any reverberation. But for the last two rows, when we use a spatial feature along with the RPS, you can see first for the normal reverberation. So whatever it is somehow acceptable, like doubled from 8 to 9 to 16 to 18. But if you look at when the reverberation goes strong, the gap between much larger. So right now the gap is like 8% absolutely. And you cannot simply fix this problem by training your system with stronger reverberation to match the case you have in test. Because when you do that, you will have some degradation on the normal cases, and the improvement on the reverberation strong cases actually does not help too much. It's only like improved by 2% absolutely. So that's a problem of our previous system of using the 3D spatial feature. So how to solve this problem? We propose to use a room impulse response to do the convolution over your mixture speech. So what we exactly do is convolve each channel of mixture speech with the conjugates of the first k frames of the room impulse response of the target. Let me explain why here it has a k. Because as we know that the room impulse response is actually a decaying function, that the magnitude is going down quickly. So instead of considering all the frames in a room impulse response, we actually only need to consider the first k frames which contribute most to the convolution. And as we know that a typical utterance will be like 5 to 10 seconds, and a typical room impulse response would be within 2 seconds. So that's the reason why over here, after the STF-T transformation, for the wave tensor, the shape is f times m times t, where f is number of frequency, m is number of channels, and t is the time index. But for the room impulse response, we have the same thing for f and m, but here the k means that only we consider the first k frames. This room impulse response is much shorter than the utterance. And then we will do a special convolution, which is named as a grouped convolution. So the grouped convolution means we will cut these two tensors by both the frequency and m into these small pieces. And we do the convolution one by one, like for each frequency and channel, we do the convolution inside and independently. So each each piece inside the room impulse response, we are only convolve with the same piece inside the utterance. This is why it's called grouped, because it's cut into f times m groups. And after this convolution, we will have a new tensor. Okay, here I also need to mention that because all these things we done are in the STFT domain, which means these tensors are also complex tensor instead of real number. So we will have a new complex tensor, and the shape of it is still f times m times t, because all the convolution is done only on the time axis. And here we further take the angle of it, which is equivalent to take the phase of a complex number. We call this RP, which stands for the room impulse response based phase. And after this, we define a new spatial feature. That is, we select two channels from this f times m times t tensor, and we compute the cosine distance between them. Okay, this diagram shows us how this spatial feature is real defined and calculated. And now I will show you why it works. So let's look at the definition of RP. RP is a phase of your mixture speech convolved with the conjugates of your room impulse response, which only considers the first k frames. And now let's assume that y is dominated by your target speaker x, so that if you expand y, it will become the room impulse response of your target speaker convolved with the clean speech xi. And now it will further convolve with the conjugates of the room impulse response. And over here, we play a small trick of changing the order of the convolution. We take the xi out and do the convolution for the room impulse response first. And to better look at this formula, we take this room impulse response convolution out and use a new term ci to denote their convolution. So ci becomes a new tensor. Oh, sorry, it should be a new sequence of length k. And if you look at this ci, you will find that the first element of this ci, the ci0, is actually the L2 norm of your room impulse response, which means let's consider that the room impulse response sequence itself is a decaying function of a complex, which is a complex sequence. And the first element is from their L2 norm, where these two sequences match well with each other. And you shift one frame next to compute ci1, because firstly, your magnitude will decay. And secondly, because you shift one frame, their phase will also mismatch with each other, making your magnitude of the ci becomes even smaller. So we can have the nice property of the ci0's magnitude will be much larger than all other parts. And also, you can see that because ci is the L2 norm of your room impulse response, which makes this ci0 a real number. And for the other numbers in the ci sequence, they are actually complex number. Here is a more concrete example. So we vary the hyperparameter k from 1 to 30 and show how the ci looks like. You can see that if you only have k as 1 or 2, which makes the sequence really short. And also because of that, the reverberation you consider will be very little. And in such cases, the CI's first few frames does not have the properties that we desire. Like at here, you can see that the first few elements of this CI sequence is also very large. But when the K goes larger, let's say you have K as 10 or 30, you can see that only the first element is large. And even for the second element, it's decaying by like 50% or even more. And because of this nice property, if we take CI back to the formula of RP over here, we convolve XIT with this CI. Because as I said, if we can ignore all the residual parts in the CI sequence and only consider its first frame, then by calculating the phase of this summation, we can only calculate the phase of the first term, where the phase of the first term is xi times ci0. And as I said, the ci0 is the real number, so that the phase of it is just the phase of your clean speech. And over here, you can see that this number becomes totally channel independent because M is on the C and C is crossed out. And because of that, if we take two different channels like M1 and M2, and we calculate the phase difference of this RP, we can find that this number will go to 0 and its cosine becomes 1. That's solve the problem of how we should cancel out the reverberations impact on our mixture. Here is the new feature we have. So on the left side, it shows the LPLs of the speaker 1, speaker 2, and 0 mixture. And on the right side is a new spatial feature, the room impulse response based spatial feature with different K. So you can see that when we increase the K generally, we can see better patterns on the feature map. Right now, this feature map much well with the LPS of your target speaker. And on this right side row, we also show the magnitude of the CI. And you can see that when K goes to 10, then the magnitude of the CI is acting as we expect, that it's only the first element is large, and for other parts it's decaying very fast. Okay, now let's use these new features. There's one thing I didn't mention before, that is how we can get the room impulse response. Over here, let's first assume that we can get the ground truth room impulse response. By ground truth, it means because we do the experiments on the simulated data, so we can actually know what is exactly the ground truth RIR is. But as you know, like in real life, it's very hard to claim that you have the ground truth RIR. It can only be if by ground truth you can only maybe collect it in advance, but all other methods actually require some estimation, and it depends on the quality of your estimation. But over here in this table, let's assume we use a ground truth room impulse response. So the first row is still the single speaker baseline as a reference, and the second row is our previous 3D spatial feature, and the last row is the new room impulse response based spatial feature, and we vary the K. And here K I use a unit second, but it is equivalently to, like, if say 0.1 second K, it means like 10 frames for a shift size of 10 milliseconds window size. So it's basically the same thing. And we can see that with this new room impulse response based spatial feature, the result improved quite a lot. And now this number is ranging from like 10 to 11, and make it very close to its single speaker upper bound. And another good thing here is that unlike what 3D spatial feature has, like we have a large gap for the normal reverberation and strong reverberation. But for our room impulse response based spatial feature, this gap is only like 1% absolutely, which match well with the thing we observed for the single speaker case, which means actually this feature works as our expectation. However, you cannot always, as I said, you cannot always expect you will have the ground truth room impulse response. So we also do some evaluation study on what if we get the room impulse response from estimation. So over here, I use the most popular or standard way of estimating RIR, that is the image source method. And I use most widely used toolkit, pyroom acoustics. But just mention here, actually for the room impulse response estimation, it's another domain which also have some really fantastic work. So I assumed I would expect their room impulse response estimation would definitely better than this one. But I just put this baseline method here because it's mostly widely used. So other than the ground truth, I also designed 2 scenarios for the RIR estimation. So for the first scenario, which I call it the best scenario, that is, we only don't know about the RT60, but all other information is known. Why it's called the best case scenario is that because this RT60 is a virtual parameter that reflects the materials of the room, which cannot be easily measured. So in reality, you cannot really guess what this number is. So in this best case scenario, I just assume this number is a random number from range from 0.3 to 0.8, which is most widely cases we've seen for like the normal rooms. And for the other things that we can measure, like the room size, the microphone absolute position, the speaker's position, for these things can be measured, I assume that we get them correctly. And the second scenario is what I call the worst case scenario. That is, we don't know anything. Actually, we don't know anything about this room. And the only thing we can know about is the microphone and speaker's relative position. And this is the basic assumption we also had for the 3D spatial feature. Let's say we go back to this position, because you can get the video inputs from the camera. Then from here, you can always get the relative position of your target speaker to your microphone. So that thing, we still keep this assumption unchanged to make a fair comparison. And with these 3 different cases, let's see how the result look like. So over here, for the ground truth, as we see that the character error rate is around 10 to 11. And for the best case scenario, I would say that the performance does not drop too much. It's only drop like 0.5 to 1% absolutely, which is quite acceptable. But for the second case, for the worst case scenario, the water error rate actually doubled, like goes to 22%, which makes this method even worse than the previous 3D spatial feature cases. And it also tells us that this method is quite sensitive to the quality of your room impulse response estimation. And how should we solve this problem? Luckily, we have some remedy, that is RNN beamformer. So we have this new diagram. And for the first few modules, they are still the same, like do the STFT transformation and do the RIR convolve to get the RPS and the room impulse response based spatial feature. But instead of sending this feature directly to your ASR module next, we insert all deep learning based RNN beamformer. So this beamformer will take this feature as input, and it will output the beamformer weights for your target speaker. And after getting these weights as your output, you will do the matrix multiplication with your mixture speech to get the separated clean speech out over here and send it to the ASR model. And please note that because we want to make the system purely end-to-end, and also we don't want really rely on parallel data. By parallel data, I mean we need to get the clean separate speech. So I don't have a separation loss over here, even though I know that the output of it should look like a separate single speaker speech. So I just use the ASR loss as a final loss to do the back propagation all the way through this whole system. And by doing so, let's see how the result look like. So the first half of this table is still from the previous result without any beamformer. And for the later half, it is when we have the R beamformer. So first, because we've already applied this R beamformer in our previous work of using the 3D spatial feature. So we know that we can get a consistent improvement from doing so. But R beamformer cannot solve the problem of this strong reverberation problem I mentioned before. So the gap here is still like large, like 3%. But when we apply this R beamformer on the Roomy pulse response based spatial feature, we can see that firstly, it's consistently improved the results and making this number even very close to the single speaker upper bound we had before. And another nice property of it is even if we don't have the spatial feature really good, like as we have in the worst case scenario, it can still largely boost our results by like 10% absolutely, and also keeps the property of having good results on strong reverberation, as we can see here, so that this normal reverberation and strong reverberation gap is almost none over here, making this even for the worst cases, we can have this new spatial feature better than the 3D spatial feature baseline on the strong reverberation. And for the normal reverberation, their number is also comparable, like the difference is very small. In this way, we can fairly say that even you don't have a good estimation of Roomy pulse response, you can always have the R beamformer as a remedy to solve this problem. And that's actually a summation of our work during the summer. And right now we are doing another try. That is, instead of using the Roomy pulse response to do the convolution, we are trying to use a single speaker's solo segments to replace this kernel. Because if you assume that your target speaker's position is not changed during the utterance, and also so that its Roomy pulse response to all the microphone arrays also remains the same, then you can always find that the Roomy pulse response of the target speaker is something implicitly inside the solo speaker segment. So you don't really need to exactly get this Roomy pulse response out. You can do the same convolution by getting a solo segment over here. And by doing the convolution, because we take the face of it, and the Roomy pulse response is inside the your solo speaker segment, you can do the same trick in such system. This is our next step. So I don't have the result presented here, but a good news is that from some initial experiments, the result looks pretty good. So this is our next step. And by doing so, another good thing is we no longer need any input on the video side. We only need the speaker to have some independent or solo parts so that we can extract such a small segment from it. This result can also be from a diarization system first to help us get to know where a speaker is doing the solo parts. So this is our next step. And I think that's the end of this presentation. Thank you. Any questions? Okay, sure.
Trying this on any like real data.
On real data, we haven't do this for real data yet, but for the 3D spatial feature, because we've done the experiments on the real data. So my expectation over here is that because we do the same for the simulation data and the Roomy pulse response feature is better than the 3D spatial features, then I expect it for the real data, it will have the same thing. But of course, yeah, we should do such experiments because the difficulty of doing such experiments on real data is so for the 3D spatial feature, you only need to collect the video information. But for this one, because I said you need to know the size of the room and their absolute position, which actually we do not measure them when we record our real data. So that's something we can very hard to test on real data. And that's also the part of the reason why we decided to move on by replacing this room impulse response kernel as the solo speaker part, because we find that it's probably very hard to really get the room impulse response from and this room information correctly in real applications. Yeah, so we haven't done that yet.
Yeah, so I guess like one of my concerns here is that like traditionally people try to ask for the late tail of the operation and not the reflection because they have the time and everything. So you can't really assume the one consistent or anything.
Yeah.
At all. There's historically there's been like methods that work very, very well on estimating the RIR if it's static, but then in practice it doesn't work at all. Like how that would work. And then also like, you know, in terms of like you're like estimating the parameters that you have your like on your table.
Yeah.
So it's like you're kind of like losing information in the top rows as you move along, but it seems to me that like you actually want the opposite, where like your RT60 is in some sense like come where kind of like early reflections are.
Yeah.
And so have you done any like experiments data like when trying to use that information rather than like the relative position? Because like, obviously like if we're talking to each other, the reverberation like definitely depends on how far we are apart, but also if we're outside, there's not going to be any reverberation at all.
Yeah.
So it seems like that feature doesn't really capture what we're doing.
But I assume that if we are speaking outside without any reverberation, then only the relative position would be enough, because now there's no reflection, then we can assume that it's a direct path. So that is the reason why the relative position means a lot here. Even in the worst cases, we still insist that this information should be fixed.
Wait, so that's kind of my question though, is that like the direct path does depend like solely on the distance.
Yeah.
But then
and also the angle. Yeah.
And then the reflections are like entirely dependent on the room geometry in some
Yes.
sense, where, like, you know, even if we're closer together, the walls are further away, the first reflections arrive at the same time.
Yeah.
So like, do you think that you're capturing?
You're right. This reason why even if we keep the relative position of the speaker and microphone, but with this absolute position unfixed, because as you said, if even our relative position does not change, but we let's sit at different position inside room, so the distance between the wall is different, then it will actually make a huge difference. We can also, like from this table, you can see that in the scenario 2, you have the relative things fixed, but you don't know the absolute position, which means the reflection is unknown. Then this result does not look good.
Yeah, that's what I'm looking at. So it's like when you start using the G4 now, but it seems to me like enough is the like early reflections.
Yeah, probably in our such simulated experiments, the early reverberation has the strongest magnitude, and for the late reverberation, because the trick we play over C is that by convolving the room impulse response with its conjugates, we make this function even sharper. Like for a normal reverberation, it probably looks like the first picture we see here, and because we now do a double convolution. So this sequence becomes sharper and sharper. And because of that, you can safely ignore the later parts. So that's like the trick over here. Thank you.
Good question. Thank you.
Thank you.